NEC section 460.8. B2 requires secondary disconnect switches for capacitors rated over 100 kVArs. In this scenario, the capacitor is rated for 100 kVArs, meaning a secondary disconnect switch is necessary. NEC section 450.3. Requires secondary disconnect switches for transformers over 600 volt amps. The transformer is rated for 225 kV amps, which is greater than the 600 volt amps. Therefore, a secondary disconnect switch is needed for the transformer as well. The 400 amps fusible switch provides overcurrent protection for the capacitor and transformer. However, it doesn't offer a means of isolation or disconnection for maintenance or emergencies. Secondary disconnect switches enable safe isolation of the capacitor and transformer from the power source. This is crucial for several reasons: firstly, performing maintenance on the equipment; secondly, troubleshooting electrical faults; and thirdly, preventing unintentional energization of the equipment. Utilizing 400 amps wire throughout the system ensures adequate conductor sizing for the 400 amps overcurrent protection. The 400 amps fuse in the fusible switch is appropriately sized to protect the capacitor and transformer from overcurrent. To ensure compliance with NEC requirements and prioritize safety, it is imperative to install secondary disconnect switches for both the capacitor and the transformer. Let's delve into a more detailed explanation of why these disconnects are so important. We'll start with the capacitor disconnect. The capacitor's primary function is to improve the power factor of the electrical system. While this is beneficial, it also means that the capacitor stores electrical energy even when the main power is turned off. This stored energy can pose a significant shock hazard to personnel working on the equipment. The secondary disconnect switch provides a means to completely isolate the capacitor from the system, allowing for safe discharge of the stored energy before any maintenance or repairs are performed. This disconnect should be readily accessible and clearly labeled to ensure it can be quickly located and operated in an emergency. Now let's turn our attention to the transformer disconnect. Transformers are essential components in electrical distribution systems, stepping down voltage from higher levels to lower levels suitable for various loads. However, transformers can also be a source of potential hazards, including overloads, short circuits, and insulation failures. The secondary disconnect switch on the transformer serves as a critical safety device. It allows for the complete isolation of the transformer from the downstream load, enabling safe troubleshooting, repairs, or replacement of the transformer. In the event of a fault on the secondary side of the transformer, the disconnect switch can be quickly opened to energize the affected circuit, preventing further damage or injury. In addition to the safety benefits, secondary disconnect switches also provide operational advantages. They allow for selective isolation of equipment during maintenance or upgrades, minimizing downtime and disruption to other parts of the electrical system. For example, if the capacitor needs to be replaced, the secondary disconnect switch can be opened to isolate the capacitor without having to shut down the entire system. This is particularly important in critical facilities where continuous power is essential. Now let's address some specific considerations for selecting and installing these secondary disconnect switches. Firstly, the disconnect switch must be rated for the appropriate voltage and current for the application. The voltage rating should be equal to or greater than the maximum voltage of the circuit, and the current rating should be equal to or greater than the continuous load current. Secondly, the disconnect switch must be of a type suitable for the environment in which it will be installed. For example, if the switch is located outdoors or in a damp environment, it should be NEMA rated for weather resistance. Thirdly, the disconnect switch must be installed in accordance with the manufacturer's instructions and all applicable electrical codes. This includes proper grounding, bonding, and conductor termination. In addition to the disconnect switches, it's also important to ensure that the overcurrent protection devices, such as fuses or circuit breakers, are properly sized and coordinated. The overcurrent protection devices should be sized to protect the conductors and equipment from overloads and short circuits, while also allowing for normal operating conditions. Coordination of the overcurrent protection devices is essential to ensure that the fault is cleared by the nearest upstream device, minimizing the impact on the rest of the electrical system. Let's talk about the wire sizing as it relates to the application. The 400 amps wire specified is adequate for carrying the load, but it is still essential to verify this with a load calculation based on the specific loads that will be connected to the transformer. The National Electrical Code, or NEC, provides guidelines for conductor ampacity based on factors such as conductor material, insulation type, and installation method. It's also important to consider voltage drop, which can occur when current flows through a conductor over a distance. Excessive voltage drop can negatively impact the performance of equipment and can even damage sensitive electronics. The NEC provides guidelines for voltage drop, and it may be necessary to increase the conductor size to minimize voltage drop, especially on long runs. And finally, the 400 amps fuse is a suitable choice for the main overcurrent protective device. This fuse protects the entire circuit from overcurrent events. However, the secondary side also requires proper overcurrent protection, typically through appropriately sized fuses or circuit breakers. The selection of these secondary overcurrent devices depends on the load requirements of the capacitor and the transformer's secondary circuits. The capacitor's overcurrent protection should be sized according to the capacitor manufacturer's recommendations to protect it from damage due to overcurrents. The transformer's secondary overcurrent protection should be sized based on the transformer's kVA rating and the voltage of the secondary circuits. The goal is to protect the transformer and the connected loads from overloads and short circuits without causing nuisance tripping. In summary, adhering to NEC requirements and implementing secondary disconnect switches for both the capacitor and the transformer is paramount for ensuring safety, facilitating maintenance, and optimizing the reliability of the electrical system. These disconnects provide a critical means of isolating equipment, protecting personnel, and preventing damage in the event of a fault. Proper selection, installation, and coordination of disconnect switches and overcurrent protection devices are essential for a safe and efficient electrical system. Now consider the specific scenario. The existing 400 amps fusible switch is currently serving a 100 kVAr capacitor. The plan is to relocate the capacitor adjacent to the existing location, which will now be used as a tap box. In addition, the feeder will be extended from the tap box to a 225 kV ampere 480/120/208 volts transformer a distance away. The question is whether secondary disconnect switches are required for the capacitor and the transformer, assuming 400 amps wire is used throughout and the switch is fused at 400 amps. Based on the NEC requirements discussed earlier, secondary disconnect switches are indeed required for both the capacitor and the transformer. The capacitor, even though it's being relocated, still exceeds the 100 kV threshold specified in NEC section 460.8. B2. The transformer, with a rating of 225 kVA, far exceeds the 600 volt ampere threshold specified in NEC section 450.3. Therefore, regardless of the wire size or the main fuse rating, secondary disconnect switches are mandatory for both the capacitor and the transformer to comply with the NEC and ensure safety. The 400 amps wire and the 400 amps fuse provide overcurrent protection for the entire circuit, but they do not provide the necessary isolation and disconnection capabilities for safe maintenance and troubleshooting of the individual components. Let's address a few potential challenges that might arise during the implementation of this project. Firstly, space constraints within the existing electrical room may limit the available locations for installing the secondary disconnect switches. Careful planning and coordination with the electrical contractor are essential to identify suitable locations that meet code requirements and allow for easy access and operation of the switches. Secondly, the existing wiring may need to be modified or extended to accommodate the new configuration. This may involve additional costs and labor, and it's important to ensure that all wiring is performed by qualified electricians in accordance with applicable electrical codes. Thirdly, the addition of the transformer may impact the overall load on the electrical system. A load study should be performed to ensure that the existing service and distribution equipment are adequate to handle the increased load without overloading or exceeding their rated capacities. If the load study reveals that the existing equipment is undersized, it may be necessary to upgrade the service or distribution equipment to accommodate the new load. Now, it's important to remember that electrical codes and regulations can vary depending on the jurisdiction. It is essential to consult with local authorities and qualified electrical inspectors to ensure that the installation meets all applicable requirements. They can provide guidance on specific code interpretations, permit requirements, and inspection procedures. In addition to the NEC, other industry standards and best practices may also be relevant to this project. For example, the National Fire Protection Association, or NFPA, publishes a number of standards related to electrical safety, including NFPA 70E, which addresses electrical safety in the workplace. Adhering to these standards can further enhance the safety and reliability of the electrical system. And finally, thorough documentation is essential for any electrical project. Accurate and up-to-date drawings, specifications, and operating manual should be maintained for the electrical system. This documentation will be invaluable for future maintenance, troubleshooting, and upgrades. It's also a good practice to provide training to personnel who will be operating and maintaining the electrical system. This training should cover topics such as safety procedures, operating instructions, and troubleshooting techniques. By investing in proper documentation and training, you can ensure that the electrical system is operated and maintained safely and efficiently throughout its lifespan. Now, I would like to provide a slightly different perspective. The information is generally valid but could lead to some confusion in specific applications. Firstly, the NEC references cited are accurate, but it's important to understand their context within the larger framework of the code. NEC section 460.8b2 specifically addresses the disconnecting means for capacitors and states that a disconnecting means shall be provided for each capacitor bank and shall disconnect the capacitor bank from all ungrounded conductors. The exception to this rule is for capacitors that are part of a motor assembly and are automatically switched with the motor. In this scenario, the capacitor is not part of a motor assembly, so the disconnecting means requirement applies. NEC section 450.3 addresses the overcurrent protection of transformers and states that transformers over 600 volts shall be protected by an overcurrent device in each ungrounded conductor on the primary side. The size of the overcurrent device shall be in accordance with Table 450.3. The disconnecting means requirement is separate from the overcurrent protection requirement and is intended to provide a means of isolating the transformer for maintenance and safety purposes. Secondly, the interpretation of the term secondary disconnect switch can vary. In some cases, it may refer to a disconnect switch located on the secondary side of the transformer, while in other cases it may refer to a disconnect switch located on the primary side of the transformer. The NEC does not explicitly define the term secondary disconnect switch, so it's important to clarify the intended meaning in each specific application. In this scenario, it is assumed that the secondary disconnect switch refers to a disconnect switch located on the secondary side of the transformer. This is the most common interpretation, as it provides a means of isolating the transformer from the downstream load. Thirdly, the statement that the 400 amps wire is adequate for carrying the load should be verified with a load calculation. While the 400 amps wire may be sufficient for the initial load, it's important to consider future load growth and potential increases in demand. A load calculation will help to determine the appropriate conductor size to ensure that the conductors are not overloaded and that voltage drop is within acceptable limits. The load calculation should take into account the kVA rating of the transformer, the voltage of the secondary circuits, and the types of loads that will be connected to the transformer. Finally, the recommendation to consult with local authorities and qualified electrical inspectors is crucial. Electrical codes and regulations can vary significantly from one jurisdiction to another, and it's important to ensure that the installation meets all applicable requirements. Local authorities and electrical inspectors can provide guidance on specific code interpretations, permit requirements, and inspection procedures. They can also help to identify any potential hazards or issues that may need to be addressed before the installation is completed. In conclusion, while the general information provided is accurate and helpful, it's important to consider the specific context of the application and to consult with qualified professionals to ensure that the installation meets all applicable codes and regulations. A thorough understanding of the NEC, accurate load calculations, and careful coordination with local authorities are essential for a safe and successful electrical project.